In this video, we are going to study definition of Fourier transform. So before starting with Fourier transform, let us revise certain concepts. We have studied Fourier series, right? So we know that if signal is periodic, we can find out its Fourier series. And if signal is non-periodic, we find out its Fourier transform. Now, there is one more difference in case of Fourier series and Fourier transform. So, in case of Fourier series, we represent x of t signal in terms of x of t only. That is, both these domains are in time domain. So, in case of Fourier series, we simply represent any periodic x of t signal in terms of sinusoidal constituent parts, but that representation is in time domain only. But now, in case of Fourier transform, we must have non-periodic signals and then we can go with the Fourier transform. Here, the major role of Fourier transform is to convert a time domain signal into a frequency domain. Now, there might be a question why we need to transform a time domain signal into a frequency domain signal. So, let us take a simple example. If we plot a sine wave in a time domain. So, let us have a simple representation of a sine wave. Okay. So, here we can only find out the properties of this sine wave, like we may have peak amplitude as a period of given signal as t. We can also find out the frequency of signal as f, which is equal to 1 by t. But if we are asked to find out what are the constituent frequencies present in the signal, see, any signal comprises of multiple frequencies. So if we are asked to find out what are the multiple frequencies in the given sine wave, we cannot find out that particular frequencies. Also, if we want to denote or if we want to find out what are the amplitudes of those constituent frequencies, those amplitudes are also not visible in the time domain signal. Hence, there is need to convert this time domain signal into a frequency domain signal where we can analyze all the constituent frequencies present in the given signal. So, we can define Fourier transform as Fourier transform is a mathematical tool used to analyze non-periodic signals that converts time domain signal into frequency domain, and it is represented as, if we have the time representation as x of t, then its frequency representation is denoted as capital X of omega, that is the angular frequency, or capital X of j omega, or capital X of f. So we may use any one of the notation to denote frequency representation, but remember here time domain signals are represented using small letters, whereas frequency domain signals are represented using capital letters. So here in time domain we are representing it using small x, and in frequency domain we are representing it using capital X. Now The time domain and frequency domain signal pairs can also be represented as, if I have a signal x of t, I can take its Fourier transform and I can obtain its representation in the frequency domain as x of omega. Same way, we can represent this equation as x of t on the line ft, which denotes the Fourier transform of the frequency representation x of omega. So we can represent the pair of time domain and frequency domain signal using these notations. Now let us see the equation for Fourier transform. So Fourier transform is represented as x of omega is equal to integration from minus infinity to plus infinity x of t into e raised to minus j omega t dt. So this is the equation for Fourier transform. The same equation can be represented in terms of f. So x of f is given as integration minus infinity to plus infinity x of t into e raised to minus j 2 pi f t dt. So this represents the equations by using which we can convert any time domain signal into frequency domain signal. Here remember that this x of omega, or we may represent it as x of j omega, it is one and the same. Only it is just the way of representing the frequency domain signals. Now in the same order we can represent the equations for inverse Fourier transform. So here x of t is equal to 1 upon 2 pi integration from minus infinity to plus infinity x of omega into e raised to j omega t dt. Remember here the sign change in the exponential. Whenever it is Fourier transform, the sign of exponential, which is the basis function of Fourier transform, is negative, and whenever it is inverse Fourier transform, the sign of exponential is positive. And here the integration is not with respect to time, but it is with respect to now omega. Similarly, if it is in terms of f, it is simply given as integration minus infinity to plus infinity x of f e raised to j 2 pi f t df. So here we are converting the frequency domain signal into time domain using these two equations. So you have to remember the equations for Fourier transform and its inverse. Using this we are going to solve multiple numericals. We are going to convert time domain signals into frequency domain, and then we are going to plot its spectrums. So remember here, in most of the cases, if signals are periodic, we go with the Fourier series representation, and if the signals are non-periodic, we go with the Fourier transform.